Good afternoon. I am Jean-Sébastien Brouillon from EPFL in Switzerland, and I will present Bayesian error and variable models for the identification of distribution grids. This means that I will show you methods to estimate the parameters of power lines and how they're connected to each other. The main message to take home here is that this is a very challenging task. If you want to do it manually, your power grid may look like this, and good luck. But you can also do it automatically using sensors. But that is also a hard problem because you have a very bad signal to noise ratio, but I will come back on this later. So why do that? Why estimate network parameters? The main motivation is to compute power flows. If you look at the power flow equations shown on the screen, they link the power injected at a node to the voltage at this node and each of its neighbors. But in order to compute that, you need Gij and Bij, which are the conductance of a line from I to J and the susceptance of that same line. These power flow equations are mainly used for optimal control, if you want to minimize the power losses or the curtailing of renewables, and state estimation. Currently, it's quite a challenging task for distribution grids, as you need to know your network, the length of the lines, the conductor type, the diameter of conductor, and the geometry of the lines, since it's generally three-phased. That means the distance between the power lines and how they're configured. This requires lots of manpower, and it may become obsolete if your distribution grid changes. Alternatively, you can put sensors on the grid and do this automatically, but this is also a very challenging task due to the high correlations between the load profiles and the low signal-to-noise ratio. Power lines have a very high admittance, which means if the line is long enough, you may have some voltage drop, but for very short lines, you don't. And in distribution grids, you have many short lines compared to transmission grids. Those sensors are also expensive, so you may not want to put them everywhere on the network, which will lead to many unobserved nodes and force you to identify a reduced network between the nodes that are actually interesting. Distribution grids are also generally very large. This is a IEEE test bench, and it has more than 100 nodes, and it's one of the smallest grids. Now, methods to automatically identify the parameters of a network have been developed for transmission grids. It is a linear regression, I equal Vy, from Ohm's and Kirchhoff's law, where I is the current, V is the voltage, and Y is the admittance matrix. The state of the art is least square, but since the Y matrix is sparse, if the topology is not known, as you can see from scikit-learn, it's usually lasso or elastic net. Now, all of these least square space methods do not take into account the error on voltages, but you have error in both variables in practice, which creates a large bias, usually towards zero, so you will identify zero admittance metrics. In order to solve this issue, we turn towards the maximum likelihood estimator, which is unbiased and take the shape of this optimization problem, where you try to find the closest I and V to your measurements, I tilde and V tilde, that still satisfy the Ohm's and Kirchhoff's law, I equal Vy, because this will not be satisfied due to the noise. This estimator is consistent, which means that with infinite sample size, you get the perfect estimate, and it's efficient, which means that you converge to that perfect estimate as fast as possible with the number of samples. But in practice, due to the changes on the distribution grid, your sample size may be limited. Those changes are mainly due to faults, maintenance, or reconfigurations of the grid, if there are new customers or customers going away. And if this sample size is limited, then your maximum likelihood estimator will have some error. And the only way to reduce that error is to introduce prior knowledge. This prior knowledge can have many shapes. It can be if you go measure a line by hand, as I explained at the beginning, then you can introduce that, that parameter value. It can also be the topology, if you know which lines are zero, essentially. And it can also be more general knowledge about the electrical model on a power grid in order to do physics-based learning, but I will come back on this later. In order to introduce any of those types of knowledge, you can use the Bayes rule and the maximum a posteriori estimation framework. This takes the shape of this optimization problem where I plug the constraint from before in blue in order to have an unconstrained problem. And Bayes rule takes the shape of this added norm at the end of a linear transform of the parameters. Now, what is this linear transform? It defines the shape of the prior. It is composed of a psi matrix and a mu vector. In the psi matrix, if you know a line, you can put a 1 at the position of this line. And in the mu vector, you can put the value of that parameter. You can also enforce sparsity by believing that the lines are equal to 0. If you know there is a line among 3 or several connections, but you don't know which one, you can also put a prior on the sum of these parameters, because the line that doesn't exist would have a 0 parameter, which doesn't affect the sum. So you can essentially believe that the sum of several parameters is equal to the parameter of only one line. You can also weigh that sum, as is shown here, with a 2 on the center column. You can enforce similarities by a -1 weight, which will believe that the difference between two parameters is 0. And as you might have noticed, I kept stacking those rows and values. This comes from Bayes rule in the log space, which is an addition. And it is equivalent to just stacking priors in the prior matrix and vectors. You can also have contradicting priors. This is very useful for switches, for example, or for this sparsity promoting prior that we developed for distribution grids. This is one type of physics-based learning where you only use the sign of the parameters S here, which comes from the fact that the conductance is always positive and the susceptance is always negative if you don't have series capacitors. And essentially what it does is the first term is an adaptive lasso prior, which is asymptotically unbiased, but with finite sample size, it creates a bias to 0. So the second term is here to constrain the L1 norm of Y, which is computed with S transpose Y here, around a hyperparameter gamma, which is not 0, positive in general. And it might be hard to tune hyperparameters, so we also provided a data-driven methods to do so using the maximum likelihood estimator. Together with that, we provided some simulation results on the IEEE test bench I mentioned before. We consider the center tri-phase parts. It has more than 50 nodes. It's around 4 kilovolts nominal voltage and had 0.01% of noise, which is about 0.4 volts. And this noise depends on the rating and not on the signal, the amount of signal. So the variations of the voltages that you can identify the network from. The line admittance is very high, which will multiply the noise on the voltage, making the voltage noise much more important than the current noise. Finally, we took 7 days of data in blocks of 1 minute of average samples because the micro-PMUs have a sampling rate of 50 Hertz. This is a lot of data, so block averaging is a way to effectively reduce the noise and the amount of data. So this test bench has the following admittance matrix represented as a heat map. With the maximum likelihood estimator, when all the nodes are observed, we obtain about 7% error. And as you can see, it's very noisy, so it's hard to figure out the topology of the network. And with the sparsity promoting prior that I've shown before, we obtain a much sparser matrix There's still 1.6% error in noise, but the topology is much clearer. Now, the work is not over, even though the results are promising. There is still some work to do on the uncertainty characterization. I mentioned there was some error, but it would be nice to have an indication on how much error there is. And this is usually given by the covariance of the estimate, since the method is unbiased. The covariance of the estimate is fairly well known for the maximum likelihood estimator, but it's not for the maximum a posteriori. So this is still some work to do. There's also work for making this batch approach in recursive fashion in order to track the changes in a distribution grid. This means that you will update the estimate with each incoming sample. There's also the influence on optimal power flow to study. So as I mentioned at the beginning, the power flow equations need those parameters, but they need the perfect parameters. So what is the influence of the uncertainty on the optimum of the power flows? And finally, how does all of this include into data-driven control? So how does the measurement noise and the correlations of the signal influence on the control performance? This is it for my presentation. Thank you very much for listening. And do you have any questions?